Hey Pre-Calc, Mr. Rashid here. In this last video, we're going to go over how to convert from word problems to functions. And this is dealing with just the sine and the cosine curves. So let's take a look at this problem. So the tide in a coastal city peaks every 11.6 hours. The tide ranges from 3.9 meters to 3.3 meters. And then suppose that low tide is at t equals 0, where t is the time in hours. And it looks like we have to write a function, sketch the graph of it, and then also make a prediction using the function, which is typically what you'd have to do in these kinds of word problems. So we're given some really good information here. The tide peaks every 11.6 hours. So what that means is, let's say we have a peak here and we are going down to a valley. We've got another peak. So the distance from peaks is often a really great measurement of the period. So the period in this case is 11.6 hours. And what we can do is take, for example, 2 pi divided by the period, and this will give us our b value for this problem. Okay, now it says also the tide ranges from 3.9 meters to 3.3 meters. So our d value, which is our vertical shift, is maximum plus minimum divided by 2. So 3.9 plus 3.3 divided by 2, and that is 3.6. So that is really great. That is our center line for this graph here. So we've got a center line at 3.6, and then a high of 3.9, and then a low of 3.3. Now visually we can kind of see our amplitude here is going to be 0.3, but let's just verify that. So if I plug that in, so amplitude is going to be max minus min divided by 2, so that is 3.9 minus 3.3 divided by 2, and that is 0.3. Okay, good. Now what else are we told? So suppose that the low tide is at t equals 0. So really now we can extend this graph here. So this is going down, and then we've got a low tide, and then this is telling me that my axis here, my y-axis, right, is exactly at this valley here. So the low tide is at t equals 0. So it starts at t equals 0. So this is also giving me now a clue that if I don't want to deal with phase shifts and things, right, I could do a phase shift, but I just don't have information how far away that is from t equals 0. But I do know at t equals 0, it's got a valley, it's got low tide. Now that matches perfectly with a negative cosine. Remember, the positive cosine goes from peak down to a valley and then up to a peak. Well, now I'm dealing with a valley going up to a peak to a valley here. So negative cosine is going to be my best bet here, and I'm not going to have any kind of phase shift over here because my valley is perfectly at t equals 0. So I can write for this now the function. So we could say the tidal height. Let's just keep using y for this. Tidal height is equal to negative, and we have our amplitude of 0.3, cosine, and then our b value, we didn't simplify it, we'll just leave it as, let's erase that. Okay, our b value is 2 pi over 11.6, and then instead of x, we're going to use t for time in this problem, and then there's no phase shift, and then we have our center line at 3.6, or our d value is 3.6. Okay, so that is the function. Then it says sketch the graph. I think we have done that already up here. So we'll see. It's just right here, C above. Okay, and then what is the height of the tide at 6.2 hours? So we would plug that in. So we would plug 6.2 into this thing here. So we have negative 0.3 cosine 2 pi 11.6. Put 6.2 in there. And then plus 3.6. And that would give us a y value. And then let's plug that in. My calculator, I get this is 3.89 or just 3.9. Is this all in feet here? Meters. 3.9 meters. So we have really a peak. So the height of the tide is another peak at 6.2 hours. Okay, very good. So that's that word problem. So let's take a look. We've got another tidal problem here. And what do we have to do anything with it? Okay, it just has the figure here. So let's write the function for this one. And we've got some really nice information. So this here, I'm assuming, okay, 1, 2, 3, 4. So maybe this is 4 here. And here we have another valley kind of, so it's 17. So from here to here, the distance is 17 minus 4, which is 13 hours. Okay, so I can use maybe that. I'm going from valley to valley. And here's another interesting thing. Okay, so let's also figure out what our max is. So our max is, remember, I kind of want to do our vertical stuff first. So D equals max plus min divided by 2. So my minimum, so it's got some really goofy values here, 1.5, and my maximum is 6.25. So maximum 6.25 plus minimum 1.5 divided by 2. Let's plug this into the calculator. So 6.25 plus 1.5 divided by 2, and I get 3.875. Okay, so that is my D value, and then let's also do my let's do the A value. So the A value is max minus min divided by 2. In this case, that's 6.25 minus 1.5 divided by 2. Okay, let's plug all that in to the calculator. So 6.25 minus 1.5 divided by 2, and that is 2.375. Okay, so 2.375 is my amplitude, and my D value of my vertical shift is 3.875. Okay, and I have a period of 13, so let's use that. So 2 pi over 13 is going to be my B value. Okay, so now I have to think about my phase shift if I want to have a phase shift. So I could do like a negative cosine and start from valley and go down to another valley here at 4. So maybe that seems like a good way to do things. So I'll go, so this will be my phase shift. So my phase shift is equal to -4. All right, this is 4, so my, actually, let's write this properly. So my phase shift equals 4. My C value equals negative of my phase shift, so that is -4. Okay, so now we have our A, B, and C and D, so we're all good to go. And we decided to go with a negative cosine in this case. We're going to start from valley and then go to another valley here. So so y equals negative 2.375 cosine. My B value is 2 pi over 13. So 2 pi over 13. And then let's use, we can use t here for time. And my phase shift is 4, or -4. So t minus 4. And then all of this plus my D value, which is 3.875. Wow, what a monster of a function. Okay, so that is for the plot of these tidal waves here, tidal heights. Okay, last problem we have. The high roller is a 520-foot diameter Ferris wheel in Las Vegas. It takes 30 minutes for the Ferris wheel to make one revolution. The riders get on the Ferris wheel at the 6 o'clock position, which is 30 feet off the ground. So let's take a look at Ferris wheels and how these things look. So we want to measure the height. So we're getting on, let's say somebody gets on the Ferris wheel down here. Then they get on the Ferris wheel, then they go around the Ferris wheel. And so the height is what we're measuring, is how high they are. Now when they get on the Ferris wheel, they are 30. Let's draw this this diagram somewhere up here. So they're on this little bucket here, and that bucket is kind of 30 feet above the ground, is what we're starting with, 30 feet off the ground. So then they start at the 6 o'clock position. That's kind of military lingo for it. That's where the 6 o'clock, the small hand is when it's at 6 o'clock. Now, the high roller has a 520-foot diameter. Okay, so for a circle, we can kind of think that, okay, this whole distance is 520, so this is like 260, and this is 260. Right, so the total is 520. So the highest person is, their height would be 30 plus 260, or 30 plus 520 would be the highest they would ever reach on this from the ground. Now it takes 30 minutes for the Ferris wheel to make one revolution. So this is really good. We're kind of given our period here is 30 minutes. So we have a period then of 30 minutes, so we can write 2 pi over 30 is equal to our B value. So that's good. Now, what exactly can we do with the rest of this problem? So here, maybe we can try this first. Graph the height of the riders as a function of time. So we know that they start at this position, so they get on the Ferris wheel and they're 30 feet off the ground. So something like 30 feet off the ground is where we're going to start. Then the riders would go up to, so they have 260 feet is halfway up that Ferris wheel, and then, well, 260 plus, let's take a look here, 260 plus 30, so this is really 290. So here is 290, and then we add another 260 to that, so this is 500. Erase this. Okay, so this is 550. Okay, so they start at 30 feet off the ground, they go to 290. So they're going to this 290, then they peak at this 550, and then they're coming back down to 30 again. And then the whole cycle repeats. So the distance between here and here is 30 minutes. And then we would kind of go through the whole cycle again. And so this would be 60. It would take another 30 minutes to reach the same spot. And so what this is really good graph, and it gives us a lot of information. It gives us that the center line here that we're dealing with is 290. And it shows us that the minimum is 30 and the maximum is 550, and so our amplitude in this case is 260. Our amplitude really matches the radius of this Ferris wheel. So it's going 260 above and 260 below, and we have the period here. And then since we're starting at a valley again for this problem, we're again at a negative cosine. So we've got here for the equation for the curve, so negative, and then the amplitude is 260 cosine. Our b value is 2 pi over 30. Perhaps we can simplify this. So let's say this is 2 pi, that cancels, so we can say this is pi over 15 is equal to the b value. So this whole thing is negative 260 pi over 15. And is there a phase shift? There's no phase shift. So this is pi over 15 times t. Let's call this the t-axis. That's our time. And then plus, is there a d value? Yes, this would be our center line. Our center line is 290. Okay, so that is the equation for the curve. And is there anything else to this? No, we're done.